Hello, this is the next video in a playlist that I'm calling Complex Variables, where we're going to explore complex analysis. And we're in the complex numbers part of this playlist. And today's topic is roots of a complex number. First, I want to finish de Moivre's theorem. And we looked at de Moivre's theorem when n was positive integers. Now we want to expand it to all real integers. And so let z be a complex number with modulus r and argument z or theta. And we covered this in previous videos in this playlist. And this is essentially the complex number in polar form. And for n an integer, this formula is true. So the complex number raised to the nth power, of course it can be expressed like this in polar form, is just r to the n, and you take the argument times n, whatever you raise it to. So again, we proved it for positive integers in the previous video. So let's first expand it to n equals 0. So the complex number raised to the 0th power, which of course is z to the 0, which is 1. But if we look at r to the 0, cosine of 0 plus I sine of 0, this is exactly 1. And that's what we wanted to show. So it does hold when you raise it to the 0 power. Now let's let n equal minus k. So it's a negative integer. So z to the minus k can be written in polar form as this. The minus k says we take it to the denominator. But now the theorem, the part of de Moivre's theorem that we proved in the last video, since this is a complex number raised to the kth power, we just take r to the k and then we take the argument times k. And now 1, we write it in complex form. And I do this because when you divide, and of course I take the r into each of those, when you divide complex numbers, you essentially take it times the complex conjugate of the denominator. So you take it times 1, and then multiply it out. And I'm not going to cover the multiplication or the division of complex numbers because we covered that in a previous video, but you get this. Well, cosine squared plus sine squared is 1. So we have r to the k squared, and that cancels with one of these r to the k's. Same way here. So this is 1, get one of those. And then we're just left with the numerator that looks like this. But that's what we wanted to show. A complex number raised to the negative integer is the modulus raised to that negative integer, and then the argument times that negative integer. And that's what we want to show. So the de Moivre's theorem is proven. Now let's look at the roots of a complex number. So a number w is called the nth root of the complex number z. Of course, this is written in polar form, if w to the n equals z, right? So that's the nth root times n, you get z back. And it's denoted by w is equal to z to the 1 over nth power. The following is the nth root of z. So the nth root of z, of course, in polar form is this, raised to nth power, is this formula here. So you essentially take the modulus raised to the 1 over nth power, and then it's this. And these are we'll just leave it at this. And so there's indistinct roots here. Of course, modulo 2 pi. Well, let's prove this. So by de Moivre's theorem, remember, I'm saying this is the nth root of z. So if we raise this to the nth power, we should get z back. And that's what we're going to show. So the nth root of z raised to the nth power. And since this is a complex number, de Moivre's theorem says just take the modulus raised to the nth power and then n times the argument or the angle. Well, the n's cancel and we're left with this. And you have an angle plus some multiple of 2 pi. So essentially you get the just this back. But that's z. So it is the nth root. Here's a graphical illustration of the complex number, and in, of course, polar form, which is this dot right here in the complex plane. right? So the angle is 6 pi over 5, and then the modulus is 3. The radius is 3. Now what's interesting is this theorem that we just showed, that if you take of course, the fifth root of 3, so that's the new modulus or the radius of the circle, then you divide it into 5 equal segments, and then you rotate these circles or the segments until one of them is a root, and then all of them are the fifth roots. And that's graphically what's going on here. And to me, that's so fascinating. Now, here's an example of complex roots. Let's find the fifth roots of minus 32. You can say we want to find the z raised to the fifth power that equals minus 32. That's what we're trying to find. So let's look at minus 32 in polar form. So it is this. So it's the radius is 32. Now cosine of pi is minus 1. So minus 1 times 32, you get minus 32. But multiples of 2 pi, the angle gets back to pi essentially, and these are always all minus 1. And the sine of pi is 0, and any multiple of that, is also 0. So this is 0. So this is the polar form of minus 32, and this is for any integer. So hence z, according to that formula, is 32 to the 1/5 power, and then this angle divided by 5, and this is it. And so if we look at the distinct values, so k equals 0, you plug it in, and you get this is one root. K equal 1, this is another root. K equal 2, of course, we get cancelations. That's 0. This is minus 1, so we get minus 2. And of course, we know minus 2 is a fifth root of minus 32. When k equals 3, this is the root. K equals 2, this is the root. And so graphically, what's going on there is if we plot minus 32 in the complex plane, that's this value, right? So the imaginary component is 0, but the real component is 32. So then you create a circle with radius, the fifth root of 32, which is 2, and then you divide it into 5 equal parts, and you rotate them until one of them is a root, and then all of them are roots. And notice that this circle on the left is minus 2, right? Because we know that's a fifth root of 32, but so are the others. And to me, that's just so fascinating. So let's look at the zeros of a polynomial. So if we have a polynomial z raised to the nth minus 1, we will find the zeros of it. That means this is 0. So it's z to the n equal 1 is essentially what we're trying to find. And z is a positive integer, and these are called the nth roots of unity, and are all given by this equation, which is, according to the theorem above, we know that. But let's prove it. So let z be this is in z in polar form, has some radius, and assume it's a solution to this. So 1 raised to the z to the n, which is z is this raised to the nth, but that is, according to Movers Theorem, it's r to the n cosine of n theta plus, that should be I sine of n theta. I missed an I right there, dang it. But in order for this to be a solution, it says that, first of all, we have to have a radius of 1, or a modulus of 1. But then this component has to be 0, and this component has to be 1 in order for this to equal 1. But that means this n0 has to be 0, because then cosine of 0 is 1 and cosine of 0 is 0. So that says r to the n is 1 and n theta is 0, of course, mod 2 pi. But the only way this to be 1 is if r is 1, and the only way for n theta to be 0, of course it could be 0, or it could be 2 pi or 4 pi. That means that it has to be some multiple of 2 pi, and this is for any integer. But to solve for theta, you divide both sides by n, and so theta has to equal this. And then we choose k equal 0, 1, all the way to n minus 1, and the result follows. And so that says this is indeed the roots of unity, or the zeros of this polynomial. So let's look at a quick example. So find the zeros of p of z equal to z to the fourth minus 1. And so we want to find z such that raise it to the fourth power minus 1 is 0. So if we let z1 be 1 and z2 be I, z3 be I minus 1, z4 to be minus I, we can raise each of these to the fourth power, right, which is this. And then the Movers Theorem says take that in 4 times, that's 1. If we take z to the z2 to the fourth, now I, of course, written in complex, or in complex number form, raises the fourth, which in polar form is this, and Movers Theorem says take 1 to the fourth times this angle to the fourth. But that's also 1 when you do the math. And you can do that the same with each of these solutions. So these are the 4 solutions, or the 4 roots of unity. And this is a big note. And so these are all the solutions of z to the fourth equal 1, or the zeros of this polynomial. And the question is why? Well, the fundamental theorem of algebra says that any polynomial, there's at least 1 root. But then there's a corollary to that that looks at the degree, and that says there's 4. There's whatever the degree is. This is a degree 4 polynomial. That there's 4 roots. Now they all don't have to be unique, but if we find 4 unique roots, and there's at most 4 roots to a 4th degree polynomial, those are exactly the roots, and it's all of them. Okay, well, I'm running along. I'm going to stop right here. Next, we're going to look at the complex exponential function. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.